Russia, Great Britain, and France had formed an Entente Cordiale. Ooh, algebra. I'll just do a few equations. No more distractions.
Hi, thanks for joining me. Today I saw a clip from The Simpsons which made me think of this classic problem. And the way I'm going to be solving this problem is using some linear algebra. Anyway, of course, with The Simpsons, you've got Bart Simpson, obviously. You got Maggie. You got Maggie's mum, who, is the margin charge, and Homer and Lisa and whoever else. But this is to do about just a town in general. So not just a family, but a town. So maybe it could be Springfield. Anyway, we have a town with n inhabitants, and it has m different sports clubs, such that each club has an odd number of members, and any two clubs have an even number of common members. So, in other words, if you take any two different sports clubs, the number of people who play both sports or members of both clubs is going to be an even number. What we want to do is show that m is less than or equal to n. Now, as I say, this is a classic problem, and this actually has quite a few different solutions, but the one I'm going to be presenting is the one using linear algebra. Let's dive into a solution. Okay, so as I mentioned, we're going to solve this using linear algebra. So what I'm going to do is for each club, I'm going to associate a vector. So we have club 1, club 2, all the way up to club m, and for each of these clubs, I'm going to associate a column vector. And this column vector is going to have n entries. And how are we going to work out what these entries are? Well, firstly, what we're going to do is number our residents. So suppose we have resident 1, resident 2, resident 3, and so on, all the way up to resident n, so the people who live in the town. And so what I'm going to do here is in my column vector, I'm going to put either 0 or 1s for the entries, and it's going to be a 0 if that corresponding resident isn't a member of this club, and it's going to be a 1 if they are a member. So for example, if I had n equals 5 and m, say, equals 3, I could maybe have 0, 1, 1, 0, 1 for the club 1's vector. Then for club 2, maybe I could have 0, 0, 0, 1, 0, so only one person is a member of club 2. And maybe for club 3 or club m, I could have 1, 1, 1, 0, 0. So what does this mean? So this means if I look at club 1's vector, this means person 1 isn't a member of club 1, but person 2 and person 3 are. Person 4 isn't a member, but person 5 is. For club 2, apart from person 4, nobody's a member of club 2. And finally for club 3, persons 1, 2 and 3? Yeah, persons 1, 2 and 3 are a member of club 3, but persons 4 and 5 are not. Okay, so this could be a potential setup. Let's check it satisfies our conditions. So each club has an odd number of members. That's true. This has 3, this has 1, and this has 3. And any two different clubs have an even number of common members. Well, if we look at these two, club 1 and club 2, the only common, or in fact there's no common members because we got 0 here and 1 here. So the person 4 isn't a member of club 1, but they are a member of club 2. And every other person isn't a member of club 2. So yeah, there are no common members here, so that's fine. 0 is an even number. Okay, let's check club 1 and club m, and we see that there are 2 common members, so person 2 and person 3. They are common members, but 2 is an even number, so that's fine. And finally, club 2 and club 3, there are no common members again. So that's fine because 0 is an even number. So it checks the conditions, and in fact we can see here that m, which is 3, is less than or equal to n, which is 5, which is great. But obviously we want to prove this in a more general case. But this setup is actually good enough to perhaps get an idea for what we want to do. The reason we wrote these vectors like this is because now we can think of them as vectors in f2 to the n, which basically means all column vectors where the entries are 0, 1, and there are n entries. So these are all vectors in f2 to the n. And now this here is a vector space, and what's quite nice about vector spaces is we can think about dimensions. And in fact, that's what's going to give us our inequality, that m is less than or equal to n. Okay, so I'm going to make a claim, and that claim is that these m vectors here are linearly independent over f2n. So firstly, what is f2n? Well, it's a set of vectors or column vectors with n entries where each vector is either 0 or 1. And the key thing about this vector space is that when you add up two vectors, you only really consider the result mod 2. So in particular, 1 plus 1 equals 0 when you're working over f2. Now, what does it mean for these m vectors here to be linearly independent? Well, that just means that, well, if I add up any combination of these vectors, so I have m vectors here, and if I take any subset of size k of these m vectors, where k is a positive integer, then those vectors, those k vectors, will never add up to the 0 vector. So linear independence is relatively simple to describe, certainly when you're working in f2. It just means that any subset of these m vectors, if I add them up, I won't ever get the 0 vector. In other words, the vector with all entries to be 0. Now, in fact, I'm going to leave the proof of this claim as an exercise to you guys. It's actually not too difficult to prove. It just comes from using this fact and using this fact. And you can actually prove a slightly more general claim, which will help you prove the original claim, and that is that whenever you add up k of these vectors, so you have m vectors here, whenever I add up k of them, I'm always going to get a resulting vector which has an odd number of 1s in it, and therefore it cannot be the 0 vector. So you can just prove that by induction on k. But as I say, I'll leave that as an exercise to you guys. So now we're going to assume that we have that these vectors here are linearly independent. But that essentially gives us our result, because if you have a set of m linearly independent vectors in a vector space, then it follows that the size of that set of linearly independent vectors, in this case m, must be less than or equal to the dimension of your vector space. And the dimension of our vector space is n. And therefore, we get that m is less than or equal to n. Now, it kind of feels like I've cheated a bit. I haven't really explained that last step in too much detail. And to explain it or understand it well, you probably do have to study a bit of linear algebra, but to at least give you a visualization of kind of why that's true. In other words, if you take any set of vectors which are linearly independent, they must be smaller than or equal to the size or the dimension of your vector space. Well, let's consider a vector space with dimension 2. So let's just consider the xy plane. So this is a two-dimensional plane. And now what I'm going to do is suppose I have 3 vectors on here. Let's say that one, let's say that one, and let's say maybe that one. Okay, and so all of these I could perhaps write down as vectors in this form, so that maybe this one here is like 5, 3, this one is maybe 0, minus 1, and this one is maybe minus a half, 3, or something like that. I don't know. But it turns out what I can always do is add up multiples of these vectors, so alpha, beta, and gamma. If I add those up, I can always end up with the 0 vector. And this is because I've chosen 3 vectors. So I can choose, obviously I could choose alpha, beta, and gamma equals 0. That's a bit of a boring choice. I can actually always choose non-zero, or at least alpha, beta, and gamma aren't all 0, such that when I add up these vectors, I will get 0. And that's because 3 is bigger than or equal to 2, the dimension of this space. Whereas if I chose a number which is less than or equal to 2, so maybe I choose 2, because that is less than or equal to 2, and maybe I take these vectors. So let me change my color just to distinguish it. Maybe I choose this vector here and this vector here. So the vectors 0, 1 and 1, 0. Then no matter what alpha and beta are, if I add them up, I'm never going to get the 0 vector unless alpha and beta are 0. But we're going to avoid a trivial case. And so it turns out that these two vectors are linearly independent. So that's kind of the reason we need m to be less than or equal to n, because if it was bigger than n, it wouldn't be true. You know, I would be able to find alpha, beta, and gamma, such that those add up to 0. So I apologize at the ending, or at least if you haven't studied much linear algebra, I'm not sure how much of this solution may have made sense to you, but hopefully if you've studied some elementary linear algebra, you're familiar with the terms linear independence. This will have made a lot of sense. Anyway, there are lots and lots of solutions to this problem. I know one is through graph theory, but I imagine there's plenty more as well. So if you know of any interesting solutions to this problem, or any other generalizations of this problem, do let me know in the comments down below. Anyway, I'm going to stop waffling for now. Thank you for watching. I'll catch you in the next one. Have a great day.